Chapter 2 is actually one of the shortest chapters of the entire class. It goes by really, really quickly, and this is actually our final lesson in the chapter. It's going to be a short video too, because all we need to do in this section is learn how to assess a dataset for normality. Or in other words, decide if a dataset that you're given is actually following a normal distribution. And honestly, this is not that big of a deal in general, as you guys will see. Before you can use table A or do normal CDF or all this stuff that we've learned about in the problem, you need to make sure your data set is actually normal. It's a very, kids get so used to, oh yeah, I'm just gonna do normal CDF. It's so easy. If a problem doesn't say it's actually normal though, you can't do that. There's a recent AP problem from a year or two ago, and it had a histogram, something like this. So very skewed distribution right here. And it asked something about what percent of scores are between such and such and such and such. And a lot of kids across the country were like, oh, it's normal CDF time. And they tried doing something that wasn't appropriate for the problem. Make sure your data set is actually normal before you do normal CDF or use that table. Okay, so that seems pretty obvious, but it's easy to get in autopilot mode and do normal CDF when you're not supposed to. So, how do you decide if a data set is normally distributed or if normal CDF would be appropriate? Honestly, in this chapter, most of the problems are going to be normal because it's what we're practicing right now. But if you're handed a data set, it doesn't say it for you. What you need to do is graph your data. And the best way to graph it, rarely will we ever want to graph things by hand. We're just going to use our calculator. So I went stat edit and I typed in all of these. These are measurements about something about a refrigerator. It's not even important what it's about, the space inside them or something like that. Once your data's in there, remember you go second, y equals, and I'm going to turn plot one on, and I'm going to start with a histogram right here, and then we'll go from there. After you do a histogram, you want to make sure you go zoom stats, so zoom 9. And it should make us a pretty decent looking shape right here. Now, when you look at one of these pictures, the scaling that they chose may or may not be the best option. So what I recommend you do after you look at this is play around a little bit with X scale, which is how much your bars go by. I would leave the min and max alone, that's fine. But for my scale, it's a 0.9, I'm gonna go a little lower, a little higher, and I'm gonna look and see if that does anything for me. So that's a 0.8. Maybe I'll even go a little lower here and try a 0.7. Basically play around with it a little bit and look at the different images so you're not fooled by a particular window where the numbers just happen to fall a certain way to make it look different than it actually does. So if I go up to 1 or a 1.1 and just try different values to get an idea of what's going on, if you do that, it does seem plausible that the data is normal. It's a lot easier to see when I was 0.7 or 0.8 in that range right there. This looks reasonably normal to me. Is it perfect? No, of course not. But when you take a sample from a normal population, you don't automatically get a perfectly normal sample, especially when you have smaller data sets. So to me, it seems plausible that this data set could be normal. There's nothing that suggests to me, hey, it's not. If I saw a super skewed graph like I drew on the last slide, then I'd be like, hey, I probably shouldn't do normal stuff here. But if it looks relatively symmetric, relatively bell-shaped, yes, it could be approximately normal. Okay, so that is the best way probably to use a histogram. Something else I want to mention right here, instead of doing a histogram, I could also choose to address this with a box plot. If I look at a box plot, and we'll do this later on in the class, second semester, so I'm kind of just planting a seed right here. When I look at this box plot, I can't tell, oh, that's normal just by looking at it. But I can tell it's pretty symmetric. It's about the same on both sides. And the box in the middle is a little bit tighter, which is good because it means more values are in that middle range, whereas having a big box and little tails would be a more spread out data set with points on the ends. There's also no outliers in this picture. So this also would kind of convince me, okay, it's symmetric, lots of stuff in the middle, less on the ends, no outliers, maybe it's normal. But honestly, for now, I would probably just go with the histogram and look at that. Okay. So the last thing we have to talk about is kind of a sidebar right here. It's a topic that's not assessed on the AP test. So you don't need to worry about this, or at least at the time I'm making this video, I don't believe it is. If it is, it won't be anything major. Called a normal probability plots. And just really quickly, a normal probability plot is taking the x values from the problem. But instead of graphing frequency on the y, what we graph is the z-score of each of our points. So it's the z-score graphed against the actual value of the point. Picture like if all these points were attached by like a string and I just like cut the string off right there and all those points fell down. If these all just fell to the bottom right here, they would pile up and make just a regular dot plots. But instead of having them pile up by frequency, we just put them by z-score. For a data set to be approximately normal, we should see a more or less linear relationship between their x value and their z-score. And when you graph them, you're going to have a lot of points packed in the middle and less so on the edges. So you can see that this data set has a lot in the middle, less on the edges, and it is pretty linear looking right here. So this is pretty linear. So the data is possibly normal. So linear on a normal probability plot means, hey, there's a decent chance that our data set actually is normal. So that's looking good. This other data set, though, same idea, z-score versus time. We cannot draw a line. It kind of spaces out this way and tails this way. This would be skewed to the right. So not a normal distribution. It's instead skewed to the right. Okay, so I won't do a whole bunch of these kind of graphs with you guys. Just realize if I do give you a normal probability plot where I graph z-score versus coordinates, you want to look for a linear pattern that tells us our data set could be normal. And on the other hand, if you see a tail to it, that tells you your data set is skewed. But if I hand you a list of data, the safest thing is just graph it on the calculator and look at the histogram, and you guys should get a pretty good idea of what's going on. And that is the end of chapter 2.